So welcome everyone. Thank you for joining. Those of you who've joined here. I mean, we've got a great webinar here that we're going to go through today, integrating 100 plus megapixel sensors, and we'll be looking at using some of the largest industrial sensors available on the market today. Our speaker today is Sam Lebo, and he'll be taking us through the content today. On the agenda, if you could jump forward. We've got kind of split up into a few sections here. We'll be taking a look at large image sensors in perspective. We'll have an opportunity to look at some of the challenges and lessons learned. So we'll open up a little bit about of what we've learned at Framos and share that with you. And we have some project examples and a product preview even that could help some of you who are interested in getting started with large format sensors. And at the end, of course, we'll have time for any questions that we can do our best to answer for you. So just a little bit about Sam and myself. So Sam is presenting today. He's a product manager at Framos. I mean, he's got lots of great experience working with industrial vision. I mean, he's going to be able to share some of his insights on things he's learned over the years working with this technology. Myself, I'm leading the product management team, and I'll be here just to host you through the process. I'll be keeping an eye on some of the questions that come in. If you could just jump to the next slide. At the top of the screen, you'll see there is a question mark box. If you select that box, you'll have an opportunity to just jump in there and add any questions you may have. We'll be tackling those towards the end of the session here and doing our best to answer those for you. But feel free to add any questions throughout throughout the presentation as information is coming in, and we'll just go through it at the end. So I think. I mean, that should be enough to get everyone started. Please, Sam, I'll hand it back over to you, and you can get started talking about large format sensors.
Thanks, Nathan. Hi, everyone. So today we're talking about high resolution and by their nature, large image sensors. You can sometimes use various terms like large format, medium format. There's lots of overlaps with, say, the photography space. So the terminology can sometimes be confusing. But our goal today is to talk about very high resolutions, some of the products up to 245 megapixels, and fairly large, like with about a 65 millimeter diagonal. And such large products come with a lot of unique challenges when you're trying to implement them into a project or a product, compared to, say, some of the smaller global shutter image sensors that many of you may already be familiar with. At Framos, we've been a longtime partner of Sony, so that's what a lot of the products in this presentation are from. And we like these Sony products because they are pushing the boundaries of technology, enabling higher resolutions with faster readout speeds, while also not compromising on imaging performance. So to put what we mean by large image sensor in perspective, I have a comparison here. The IMX250 is an extremely popular global shutter sensor machine vision. That's a 2/3 inch optical format. And the IMX661 is 3.6 inch optical format. But what's great about them is that they actually have a common pixel size, and imaging performance characteristics are quite similar between the two. So if you're designing an optical system using global shutter sensors, you can actually do quite a bit of work prototyping with these smaller, less expensive sensors and scale up depending on your project needs. Things are a little more complicated in the rolling shutter domain, where you do have a 3.76 micron pixel available in many resolutions, 20 to 150 megapixel. But at the highest end, the IMX811, it uses a smaller 2.81 micron pixel, which is there's no direct comparison in a smaller format. So something as simple as measuring imaging performance really has to be done on the actual sensor. It can be dangerous to make too many assumptions. putting a lot of these sensors side by side, you can see that there are some commonalities in terms of footprint, but otherwise the pixel sizes can be different. The diagonals are fairly similar. Sony has put a lot of effort into creating a smooth transition path for customers who may have used the IMX411 previously to the IMX811. So the diagonal is similar, but not exact. And the package is the same physical outline, but the pinout is different. But a key enabler for all these sensors is the readout interface. In these cases, it's SLVS EC, which allows for very high speed readout over fewer lanes. And with each sensor generation, Sony's been increasing that readout speed, allowing for more and more data over the same number of interfaces, or in some cases, increasing the number of interfaces at the same time to further increase bandwidth. Or with the IMX811, despite that higher top speed of 9 gigabits per second, they also support the slower speeds. So if you're using a system that was designed around the 411, you can use it in a backwards compatibility mode over 16 lanes instead of 8. Generally, the imaging performance of these sensors is consistent with Sony's excellent quality, and the ADCs allow for extended bit depth compared to a lot of the other sensors in smaller resolutions or for other applications because of the high-end nature of these sensors and targeting more specialized applications. That extra bit depth is typically appreciated. So when it comes to actually integrating these sensors, there's quite a bit of additional complexity beyond your typical CMOS sensor integration. More voltages, the sensitivity to their impact on image quality is typically higher than integrating a rolling shutter sensor in a security application. Designing for manufacturability is another big item because your ability to iterate on these products is more restricted just by the cost and potentially lead times. And also the firmware side is something that, to deal with such high resolutions and high data rates, you do need to master that SLVS EC interface to get the most out of it. We'll go over that in a bit more detail. So many of the problems inherent to using large image sensors are common across all image sensors. However, their effects and the steps needed to account for them are say exaggerated or taken to the extreme. So things like centering and rotation, you pretty much always have to do that in any optical system. However, the potential impact of something measured at the center versus measured at the edge over such a large array becomes more problematic as the array size increases. And often these sensors are used in very specialized systems where the lens mount itself may not be a typical C mount. So as you're defining how the product is mounted and calibrated or evaluated during the production process, a lot of these systems need to be designed bespoke for that imaging system, or they need to be designed to handle such a large product. Similarly, tilt has the same problem, where tilt within an image sensor is typically defined as degrees. So the further out from center you are, the more extreme the effect. Typically, the way that this can be most effectively handled is with some sort of active alignment system designed into the product to best pair the sensor and the lens. And there you also have to carefully choose your reference plane, whether it's a PCB that the board has been mounted to, or whether it's the center or the image sensor package itself. Can have a big impact on how much variability you need to build into your system, or what the calibration process might look like. And then also lens selection is something that is quite a bit more variety than typical machine vision, where C mount is the dominant lens mount interface, and in embedded vision we use M12 all the time. We find that with these large image sensors, most end projects are using something custom or semi-custom, but there is still a need to evaluate the lenses or the sensors with a lens early in the project. So that's where things like F mount, M52, or the V mount, those are all have a sufficiently large opening to deal with these lenses, even up to around the 65 millimeter diagonal. But like I said, typically you're investing significant amounts into this project. So an off-the-shelf lens is good for those initial prototypes, but in the long run, as things scale up, to really get the most value out of using a high-end sensor and very expensive optics, customization is pretty typical. And then that can open up things like, okay, how are those tilts and alignment managed, and whether the mount is not standard at all because it's designed to get right up against that back element, or with some other special features that are specific to the product you're designing. The SLVS EC interface is something seen on most high-end, and particularly in the industrial space, Sony image sensors. The latest version of that, we have SLVS EC 3.0, and then on future sensors 3.1, is around 9.5 gigabits per second per lane. And this can be a substantial improvement over the kind of massively parallel LVDS implementation of a lot of other large high-resolution image sensors. It allows for kind of automatic skew correction across the different clock lanes, and generally simplifies your PCB design. So there are some complexities on receiving this data on the FPGA side. That's something that Framos provide an IP core for AMD FPGAs. And it is something that can be done yourself based on the SLVS-EC spec from the GIA. Typically, this is a problem that customers tackle. It takes effort, but it is something that if you want to get the most data out of these high-resolution sensors, you're going to have to figure out this interface. Specifically on some of the largest and newest sensors like the IMX811, there is a unique arrangement. So this particular sensor has 4 different groups of 4 readouts. And what that means is you read out 2 pairs of each if you're using SLVS-EC 3.0 at 9 gigs per second. Then you can receive all that in your FPGA, and some additional processing is required to align the data from the different readouts. It's not too different from some of the old CCDs where you have multi-tap readout. Here, it is all in the digital domain, so there's no balancing required, but you do have to align the data, which is something you don't have to do on other sensors like the IMX411. And this is something that is described in the sensor datasheet, and Framos has experience enabling our customers to do. It's also part of a reference design that we've developed that I'll talk about coming up later. When it comes to powering the sensors, the larger and larger arrays, they do have simply more voltages that need to be supplied to the sensor. And we find that even if you are familiar with powering these smaller sensors like IMX250 I've mentioned before, typically these sensors are used in applications that are generally more sensitive. So when scoping out a project like this, it's important to give yourself the resources and invest in things like power supply for your image sensor product. Because if you realize that you've underspec'd one of the power supplies, or the filtering is insufficient, that'll set you back quite a bit, because iteration when you're dealing with such large image sensors can actually be a huge challenge for these projects. As soon as you need to do a second run of your PCB and have that populated with a sensor, that's massively more expensive than using a small half-inch, 2/3 inch sensor. It is all orders of magnitude more expensive with longer lead times. So iteration is expensive both on just pure cost, but also it potentially impact a project schedule. So we give our customers, kind of sufficient caution, like these are more complicated, they need to be carefully managed. And in extreme cases, if sufficient attention is not paid early enough in the project, you can end up with potentially, row noise, column noise, whatever, however those mistakes have kind of crept in. And you also need to be mindful that the way that you actually measure this also needs to scale with the resolution. So for example, the tools that you may have already designed around C-mount system development, now you need to scale up your tools to actually capture those images, have a uniform black plane or a uniform gray plane. Things like your light tube you might need a larger one. So that's where potentially working with partners that are already familiar with developing these types of systems can add value and help you de-risk your project. Additionally, when it comes to physical PCB production, with a larger sensor, a larger board comes more problems. The way that the sensor itself is heated during the reflow process needs to be very tightly controlled. Obviously, the reflow information is included in the sensor data sheets, but if you're working with a manufacturing partner, the cost of iteration is just not comparable to a lot of other image sensors. You're doing potentially panel sizes that are 1, maybe 2 sensors per panel. So your ability to generate kind of statistical data is much more limited. And again, failure is expensive. You might not want to buy an extra 10 sensors to support your initial production run, or you might buy that many expecting a certain pass rate. And if you're not able to meet that, to reorder more sensors you're not expecting to keep a lot of these on the shelf. So you have to either carefully forecast, be very typically conservative with how much your inventory is being buffered. It has to be carefully managed, and these are typically problems that are just a manageable cost with other camera projects. Additionally, depanelization is something risky. Depending on how it's done, whether it's a router or a cutter, you definitely don't want to crack any of those BGAs connecting the image sensor to the board. But also in the thermal space, you actually might want an even larger board to allow for more copper to conduct heat. But you also need to use potentially certain PCB materials that are less prone to thermal expansion, so that as such a large piece, temperature cycles as the image sensor heats up and down, or maybe you're cooling it to reduce noise, that can create additional stresses on the board that need to be taken into account during the design. And also quite common on some of these boards is to have a cutout behind the image sensor, because there's a large area without any pins. And that's typically used so that the sensor can be attached to a heat sink from behind, which has a lot of benefits. But now you've also created some risks that your PCB is not as rigid before because there's a big cutout in the middle. So this is something that, again, you have to be quite careful of during the design phase. Talked about image quality before, and that's something you have to measure. Here we have an example of EMBA 1288 measurement equipment. This particular one was designed for C-mount sensors and smaller. So as I mentioned before, if you are moving into large image sensors for the first time, a lot of the equipment you have may need to be updated and expanded. That can increase project costs. Some imaging performance can be done on that smaller window, but you need to kind of be mindful of how you interpret those results. Things like linearity obviously would not be representative of the whole image sensor. At Framos, we have an extensive experience helping our customers with sensor integration as a Sony distributor, but we also have helped our customers scale up some production systems using these image sensors by providing additional value through things like sensor module design and production of those sensor modules, as well as things like the SLVS EC IP core and some reference implementations of these sensors to allow our customers to get up and running much more quickly. Now I'll go over some example projects we have showing how we've helped our customers implement these sensors. So this first one here is an example of IMX 455, which is a smaller version of the 411. And our customer wanted to use this with an NVIDIA Jetson using a single cable solution. How that was realized is a board adapting the SLVS EC interface of the sensor to GMSL. Because the Jetson itself uses a MIPI as an input, they use GMSL as the serializer-deserializer bridge. And we were able to use our existing experience with the SLVS EC IP core running in an FPGA to handle that image, do the image receive, and then convert that data stream to MIPI, which could then be serialized using our existing GMSL serializer board. So the project risk was reduced by leveraging our existing IP core, but also our existing GMSL boards. In this case, we used an AMD FPGA. And for thermal management, there's a significant amount of exposed copper on the front and back of the image sensor PCB. Since images are always appreciated, here's an example here where there's a bit more cables than you would normally expect, but that was an advantage in this project because we were able to, again, by leveraging existing products, we were able to put prototypes in the customer's hands faster. So things like the data connector is separate from the additional power that needed to be provided to the image sensor board from the conversion board. Looking at even higher resolution sensors, we have done some projects with the IMX 811. Some of the initial kind of requirements there was how do we enable customers to even evaluate this sensor? It's an expensive sensor. It's quite bespoke in many ways. So for somebody to justify at the early stage of a project, is this sensor going to work for me? To find that out is quite expensive. It can be a significant amount of development resources needed. And then also if you're developing just a test platform, that effort doesn't all transfer over to production. So Framos was able to help the customer out by providing a design that could be used for evaluation, but was also validated as part of a mass production process so that it was repeatable and reliable. And it built on our existing expertise in prior projects using similar sensors for other custom solutions. So the product we developed is a quite unique looking sensor board that allows for 8 lanes SLVS EC readout with separate power and control cables. The image sensor board itself was designed not with kind of screw holes for mounting, but it's more designed to be floating. So we talked about imaging, centering and rotation before. Here, the reference plane is the image sensor itself. And there's even a cutout on the back to attach a heat sink so that the thermal transfer can be managed. For early testing with FPGA dev kits, we have a custom adapter board shown here as well. As part of a reference design, we needed to provide a bit more of a complete package. And here, what we've implemented is both our SLVS EC receiver IP core, as well as some additional functionality to recombine the data from those four interfaces I mentioned before and convert the image suitable for display over HDMI. So this allows for a pretty quick way to verify that you're not just getting a test pattern or blank image. You can actually see on a monitor that whether the image is coming through correctly or something is not working. Some more pictures here of our development boards, and as well as shown with a large Pentax lens as an example. This is a development kit that will be made generally available later this year. And it includes, or is available as either just components like the module, if you have a specific optical system in mind already, or as a full reference implementation with the fixtures, with the adapters and all the cables, and our reference design software. So we're excited about this because we see that we're enabling more people to pursue projects with these types of sensors by reducing the project risk, allowing us to share our expertise with our customers and help get you to market faster, or maybe pursue projects that were maybe a bit too intimidating because this type of image sensor was not your comfort zone. So we look forward to many interesting projects with these sensors in the near future. Now turn it back over to Nate for our Q&A.
Excellent. Hey, Sam, that was awesome. Thank you so much. And a lot of great detail there. As such, we did get quite a few questions coming in. Actually, let's take a peek at a few of them. First off here, we had a question come in asking if you plan to elaborate on current lens testing options versus what's coming next in terms of custom or optimized lens designs.
So as a sensor supplier and camera manufacturer, we focus on how do we provide our products in a package that is most flexible for the ways people are trying to use it. So often that manifests with trying to leave as wide of an opening as possible and a flat reference plane. An example of that is that reference design dev kit I showed at the end, where the lens mount adapter itself is, it's a separate component. It can be removed and you can attach whatever lens mount you want on there. So that example was the Pentax mount. We've prototyped F mounts. And then I think our production version of the dev kit uses a V mount.
Great. Good. Some other question here. This is related to SLVSEC. Someone was asking, is it possible to share the VHDL code for the SLVSEC interface? So maybe an IP core question or related, right?
Yeah, our IP core is available either as closed source, as a kind of black box IP core, or open source under different licensing. That is a solution that Framos sales can provide you more detail about, and it's definitely something we can provide under the right terms.
Yeah. Reach out, and we'll find the right way to sort you out. Good. So here's another one here. Can you explain a little more about the source of the line noise that you highlighted on one of the slides? So this is the power supply design. Is this a simple offset or an FPN?
In that case, it would not be FPN. It would be some amount of power supply noise, like a ripple, which means it's more variable across the array compared to FPN, which is a specific line having a specific offset from its neighbor that can be corrected using flat pattern correction. But more often it's an analog noise from the power supply circuitry, where if a shortcut has been made on the filtering or some incorrect assumptions were made, where the impact on a particular line is variable, so calibration is less able to handle it.
Perfect, great. And I'll just take a couple more. I know of a few more actually came in here. We won't be able to get to all of them, but we will we'll take two more here just quickly. Here's an interesting one, Sam. It's related to the IMX 811. Is there any experience with cryogenic cooling of the IMX 811 sensor to obtain the lowest possible dark current? So, you know, kind of liquid cooling or, you know.
Uh, I, I, I don't personally have experience in those implementations. Typically, those cooling solutions are being implemented by our customers on their own custom designs, where we're supporting them as a sensor distributor. However, the sensor itself is able to operate at lower temperatures. Typically, the imaging performance specs published are at ambient temperature. Um, so unfortunately, I don't have any more say firsthand details in those types of solutions.
Great. Yeah, I mean, that's an interesting one. I mean, yeah, we haven't gone to that extent here, obviously, at Framos, but it's, I mean,
There are
interesting
lots of
concept.
solutions available from our partners and customers that are doing sensors implemented for building scientific cameras with these sensors, and often they are implementing some sort of Peltier cooling or active cooling.
Hmm. Hmm. Okay, last one here. So just on, I guess, on the last product you were showing, when will that IMX 811 module be available for customers? Um, will the reference design kit also be released at the same time?
Yeah, so the module and reference design kit, we're going through a production process right now, and we're expecting it to be available around the end of August. Um, yeah, and that
Great.
includes both the module boards themselves, as well as the full reference design with the supporting adapters and mechanicals and software.
Excellent. All right, we look forward to it. Again, I saw some other ones come in here. We're going to have to cut the Q&A now, but we'll follow up for sure, just by email. So if you could just jump to the next slide. I just have a couple quick comments to make on some future presentations that you guys can also get involved in. I mean, upcoming here on July 24th, we have a Sony Pregis S sensor evolution with Sony. Also getting later in the year, October 8th, optimizing advanced Sony sensors, specifically in agriculture. And I'll touch on one more here. We have an in-person event as well that I wanted to make everyone aware of. It's called Imaging Next. It's put on by Framos in Munich. We're offering this for people to sign up. Please, you can see it on our website. Please jump on and take a look, or get in touch with us. And this event is happening September 18th and 19th in person in Munich, and we'd love to see some of you there. So we're going to cut it there. Thank you very much for everyone who joined, all the great questions. Thank you, Sam. That was a lot of great information. Clearly, everyone was very, very engaged on this one, so well done. And we hope to see you guys more. If you want to get in touch with us, check us out at framos.com.
Thanks, everyone.
Thank you.